Hello people, my name is Philip Taylor. I work for a company called Fabric Technologies, and we're building a web technology for multi-threading web applications. And this is Peter Zion.
Peter Zion.
Yeah,
Some of you guys.
and this is our lead engineer. So before we talk about anything we're working on, we want to sort of provide some background and explain sort of the motivations and what brought us to start working on technology for web applications. We typically work in high-performance software, and what we've been aware of is the changing hardware trends over time. What the different CPU manufacturers are producing each year has been changing significantly, and especially in the last 3 to 5 years. So here's a comparison of two different CPUs. The Intel Pentium 4, which was released 2009, ran at 3.8 gigahertz. And it was a very complex CPU, very fast, ran at a very high frequency. But next to it is the Intel Core i7 processor, which was released fairly recently, and runs at roughly the same frequency. Actually, it runs at a slightly slower frequency. The key distinction here is that the Core i7 processor has 4 cores built into it, and it's a processor built around a different paradigm. Instead of trying to speed up, make one processor core go as fast as possible, they've introduced multiple cores, and actually they're running the cores at a slightly slower frequency, but instead, by utilizing all of these different cores, we get higher performance overall. So this is stepping forward a bit further. Just recently, this processor was announced by Intel. It's called Knight's Corner. It's got 50 cores in it. And I don't actually know how fast, what frequency it runs at, but this is sort of a peek at the future. Like, let's look forward 5 to 10 years, and this could be what we're looking at in terms of a consumer-grade processor. This sort of transition is what we've seen actually happen over the last 10 years from sort of more basic CPUs that people use in consumer devices. And this is taken from an article in Dr. Dobbs' journal. A guy called Herb Sutter wrote this article, and this graph sort of plots the changes in hardware over time. I mean, it's got the Pentium 4 processor mentioned there, and it's contrasting different properties of a CPU architecture. One of them is the frequency, and we can see the frequency is that dark blue line. And for a decade, or the decades prior to 2005, we saw a pretty consistent increase in frequency of CPU processors. But things have changed over the time. Due to physical constraints, actually increasing the processor frequency just isn't the solution to the speeding up of processors in the future. And instead, what we've seen is actually leveling off the CPU frequencies, and conversely, the other line that's important to notice is the green line, and this shows actually, what is it?
Number of transistors.
Number of transistors.
It's actually the only thing which has remained constant is, of course, Moore's law, which actually wasn't about speed. It was about how many transistors you could get onto an expensive silicon. And as you can see, Moore's law continues to be true to this day. But if you look at the pink line at the bottom of the graph, which is the actual numerical performance of these processors, it's pretty much leveled off. And I think this graph, when does it stop at there? 2005. Or like basically the last 10 years, numerical performance on a single core has basically remained constant.
And I think what we're looking at this graph and saying, well, what happens if we extrapolate this graph forward a few more years? What is this delta between sort of the gains, the performance gained by a single core versus the performance gained by multiple cores? And actually, as we can expect, the delta between sort of the power we can extract from a multi-core processor is going to be significantly more if we can utilize all of the cores available. And there's been some other developments happening recently as well. So this is a shot of the GeForce GTX 200 GPU, and what I wanted to show here was sort of a contrast showing, okay, we've been looking at Intel CPUs, and here is a NVIDIA GPU. And what we can see there is some numbers. It's got 240 processing cores. And as we know, these are different kinds of cores, but there's still lots of them. This is a massively data parallel processing engine. It's capable of processing vast quantities of data very quickly. And it's just another computational resource that we have in consumer-grade machines today.
One of the things which is really interesting about working with GPU processors, which I'm sure many of you have here before, is the GPU processors, there are a tremendous number of processing cores, but the cores actually are not running at a clock speed which is very comparable with the CPU on your machine, which makes a lot of sense. But one of the things that implies is that really, if you want to be using these processors in any meaningful way, you really have to be able to split up your problem into lots and lots and lots of things that you can do in parallel, as opposed to having single tasks. We know that, of course. One other thing here is that, as you're aware, is that the actual memory architectures of these chips are fairly sophisticated, and it's a programming model that a lot of programmers are not even used to working with.
And this is a graph pulled off a blog comparing the floating point capabilities of the Intel chips versus the NVIDIA GPUs and the ATI GPUs. Now, this is the kind of graph that NVIDIA and ATI love to see because it makes their processing capabilities look extremely impressive. It's a different form of processing capability. It's not as general purpose as the CPUs. But what it shows is that to really leverage all of the computation power in a machine, you really have to be able to take advantage of the GPU. The GPU has evolved well beyond just a graphics processing unit, and it's just another compute resource. And so the concept of heterogeneous computing comes in, where you actually have to divide your tasks into ones that can be solved on a GPU versus ones that need to be solved on the CPU. And this is kind of another step sideways. So there's lots of changes changes happening in hardware, and one of the more impressive changes that have been happening over the last year is the mobile chipset front. What we're looking at here is some changes in chip architecture over the last few years as they've packed more and more cores into a smaller chip. Here we have a dual-core Cortex A9. This is running 2 ARM chips, but it's also got a GeForce GPU on it, so it's running an NVIDIA GeForce chip. This GeForce chip can run OpenCL code, and it's a fully-fledged graphics processor. This is the kind of capabilities we didn't see in anything except for sort of fairly high-end gaming machines sort of 5 years ago. So what we're seeing is that while we're noticing these big trends happening on the main sort of processing architecture front, the mobile chipsets are catching up really fast. Almost every single, well, all of the major mobile chip manufacturers have announced quad-core chips, designs, and these will be coming on the market towards the end of this year.
A lot of the stuff is actually available today. I went to FutureSoft the other day and picked up an Acer tablet, which was dual core with very powerful GPU, and it's $500 there. So, impressive.
Now, at the same time, we've got the markets are changing in terms of the software. 7 or 8 years ago, all the developer had to think about was building software that would run on an x86 chip on a single core on Windows operating system, and they were done. They could basically target a huge market just like that. But things have changed. We've got operating systems such as OS X have become much more prominent. They've had a huge gain in market share. There's new operating systems such as Android coming on the market, which have their own peculiarities, and QNX and iOS. So for a software developer, not only is the hardware changing, is a huge technical challenge to handle, it's also the software platforms, and actually making software that can run on a variety of software platforms is another technical challenge which developers today are facing. So this is basically leading to an overall increased complexity in software development. This complexity really relates to people trying to build high-performance software, anything which really effectively uses the hardware capabilities. We've got many core architectures coming out, and people need to be able to write software which takes advantage of these cores. We've got different kinds of cores in the same devices, GPUs and CPU cores. And this is leading to developers actually having to work with multiple languages, things like OpenCL, CUDA, C++, Java. There's just a lot of different tools that people actually need to be very competent with to be able to access all of these capabilities. And the hardware fragmentation is a serious problem. Things like ARM chips versus x86 chips, the same machine code actually won't run on the 2 different processors. And then the software fragmentation. As soon as you're accessing operating system services or using operating system services, then you actually have to start paying attention to the actual operating system you're running on. And this is a massive challenge for developers too. So we see actually the work that a developer has to do in the next few years to actually leverage all of this hardware is extremely complex, and much more complex than what they had to do 6 or 7 years ago. Now, we're going to talk about web technologies more now. And web technologies have some massive benefits over the native code applications. And one of the reasons is because they use platform-neutral technologies throughout. Web content can run on pretty much any device which is capable of rendering HTML. And, but it sort of comes at a fairly heavy performance price, and that's what we want to talk about now. So we did a lot of research just looking around at sort of data and statistics, trying to find content that would complement this talk. And this is a graph which plots, over time, the speed of various scripting engines. And what's nice is that the graph starts way back at 2007, and we could see the red line there actually represents ActionScript. So it's a proprietary language developed by Adobe. And all these other bars are actually representing the speeds of various scripting engines. And what we can see is a massive arms race, led nicely enough by Google, but it's actually pushed a lot of the developers and vendors to really speed up their JavaScript engine significantly. This particular test does show Chrome way up in front, which is good, but we're not going to go into that little discussion. The sort of the takeaway point here is that we have seen massive advances in the processing speed of JavaScript engines. But this is sort of the downer slide. Like this is kind of comparing. Although we've seen huge performance increases in JavaScript, when we start comparing it to native code, it still pales in comparison. So this is actually this is the same test. I can give you the link to the article if you want to have a look at it. But basically comparing a variety of different JavaScript engines versus native client. So it's a plugin architecture developed by Google. But it's running native code in the browser. So the top 7 bars represent various scripting engines, and the fastest one in this chart is actually the Chrome 11 V8 engine. And then we've got the lower 3 bars, which is basically the native client running sort of the same code written, I think, in C and on Linux, Windows, and OS X. And anyway, you can see we're not going to go into the numbers too much, but there's still a massive delta between the two. So in the web community today, there's a lot of optimism around JavaScript and the web technologies, and because we've seen so much advances in the performance of JavaScript, I think some people are still expecting that eventually the gap between native code and JavaScript will disappear completely. And what we're saying is, well, it has sped up a lot, but the gap is still there. And in some cases it will speed up to this close enough to native code that people won't mind, but in many cases it will be well behind. And the gap today is still significant.
Okay, maybe I'll talk specifically to the slide. So if we actually think about what's happening in, for instance, a JavaScript runtime. JavaScript runtimes are extremely sophisticated. A lot of this, I think, is thanks to Google's V8 effort, and other JavaScript engines such as Firefox has been playing catch up on that and doing a really good job with it as well. Obviously, what's going on behind the scenes to make it possible to achieve these increases in runtimes are a lot of static and dynamic analysis within the engine itself, and in cases where you're actually able to see that for a certain part of the code, the type structure doesn't change, you're actually able to just compile it to fixed native code, which you can just execute directly on the processor. That works really, really great, especially for things like isolated unit tests, where you know that there's no complexity to the thing. But one of the problems with JavaScript is JavaScript has a weak type system. If you write your code perfectly, then it can compile it to really tight native code. But if you make any mistakes in doing it, it can suddenly fall back on weak type execution, which, as we all know, basically just means the code is being interpreted at that point. In comparison, of course, we all know that a compiled language like C or C++, we know absolutely everything, exactly how memory is going to be used. We can optimize it specifically for the entire program, for instance, compile it directly to native code, and this is why we're seeing the performance numbers, which we saw in the last slide. There's some other things which sort of add to the complexity of the situation. in a scripting language like JavaScript, you don't have very much control over the actual memory architecture. For instance, the way that the memory is, the data is laid out in memory. You can, for instance, have problems where, because it uses a much more complicated structure to represent arrays or something like that, you lose the performance that your caches on your processors would otherwise give you, things like that. And there's just very little control from a scripting language of that kind of thing.
And so Peter's talking about the concept that if you were to write very clean JavaScript code, and in theory the engine could actually analyze this code and produce extremely efficient jittered code, or sort of the machine code. But the performance metric we were looking at before was a quicksort. So it's not a sloppily written test. It's not your sort of run-of-the-mill JavaScript you find online. This stuff should be really tightly written. So this kind of should be actually an ideal case for the optimizer to produce the fastest code possible. In many real-world tests, we'd expect much worse delta between the two languages. So this is kind of summarize the position we're at. We've seen lots of increases in the performance of JavaScript over the last few years. This is great. This is good for everybody. This is good for web developers, and it's expanded the capabilities of the browser to build much more sophisticated web applications. It's still playing catch up on single-threaded native code. And there's debate that maybe it will catch up completely. But at the same time, we're seeing if you're writing native code today, then you should be writing multi-threaded native code if you really care about performance. So the delta even between native code and multi-threaded native code is actually pretty strong. And this is sort of where, in the industries that we've been working in, visual effects and video games, we've been realizing you must take advantage of multi-cores to create a distinctive advantage. And on the right bar here, the red bar, which is supposedly the best one, although I've been told never to use red for a good thing, is code which uses the vectorization, vectorized code which runs on GPUs or if you can actually get your problems to be solved on a GPU, you've got a massive performance increase again. And ideally, the best scenario is actually where you're using both multi-threaded CPU code and using vectorized code whenever possible. So now we're going to talk a little bit more about, we've talked about the hardware, we've talked about JavaScript a bit, but how do you take advantage of these new architectures? What are the best practices in terms of making the best use of the hardware available? So there's a concept called task-level parallelism, and this is your first introductory method to utilizing multi-core architectures. What you do is you take your program, you break into pieces, and you try to solve each piece on a different core. You try to isolate your tasks so that there's not too much interdependencies between them. Ideally, there's zero interdependencies, and then you can basically solve these tasks in parallel. Then you do that a few more times, and if you can break your program down into enough tasks, then you can actually distribute these tasks across all your cores. There's a few challenges to this approach. One of them is not all problems can be easily broken down. The granularity to which you can break down your application defines the limit to the number of cores you can actually utilize at any one time, which is that's a heavy problem, and often the longest running task you have will end up becoming a bottleneck for your application. And there's another method called data level parallelism, which is where you take one large piece of data and you divide it. You have an operation which you want to do on this data, and you divide the data into pieces, and you actually allocate the different pieces to different cores. And this actually scales very well. This scales to many, many core architectures because usually you're working on enough data that you can slice it into hundreds of pieces and allocate them to different cores. And this is basically the way that the GPU executes code. The task level parallelism is really great, and it's a good first step in terms of multi-threading, but it really only goes so far. And then data level parallelism is a way to scale across many, many cores, but it also has a drawback that it tends to be limited in the kind of problems you can solve with it. Not all problems can be solved using data level parallelism. Lots of problems don't involve large data sets. Lots of problems are just actually better solved in a single core all at once. So when we're talking about high-performance software, there's a few things that there's sort of conclusions from the previous slides. High-performance software really must run native code. There can't be an intermediary layer between your executing code and the actual chip. This intermediate layer does have a pretty heavy performance price, and we've seen from the numbers that this is not insignificant. It really must utilize the multi-core CPUs. If you've got a quad-core chip and you're only running on one core, that's a 75% wastage of CPU cycles. And if we extrapolate further, that fraction of wastage will get worse and worse over time. You must utilize the GPUs. If the GPU is going to represent a huge advantage in terms of computation, by simply not utilizing it, you're just leaving a lot of processing on the table. And due to the fact that we have such rapid advances in hardware technology today, you really have to be able to build a system which can adapt to the changing hardware. If you're building a software today and you want it to be running for the next 5 years, you can't assume the structure of the CPU that's going to be running on. So you have to be able to build something which is adaptive. You can't hard code it to any sort of particular CPU architecture or GPU architecture. And of course, due to the fragmentation in the software platforms, you really have to be able to build something that's cross-platform, and this is a huge challenge on its own. So there's other aspects here. Leveraging the internet today seems like a no-brainer. There's massive amounts of data and computational resources available online. And if you're building something that is pushing the limits of performance, then you must consider using these extra resources. And this kind of list defines a very technically challenging problem set. And there isn't many companies in the world who have engineers capable of solving these problems. And this is what spurred us to start building Fabric. So Fabric is really about high-performance web applications. When we say high performance, we mean high performance in the raw form of the terms. We don't mean relative to JavaScript performance. We don't mean relative to what you can get today. We mean very high performance. If you're building a desktop application, what would be the performance benchmarks you'd expect to hit? And if we can get those same benchmarks in a web application, we have truly high-performance web applications. Now, I'm going to spend a bit more time selling why would you even care? Why would you even care about high-performance web applications? I mean, we can browse the internet, we can look up Wikipedia. What else do we need to do in a web browser? Well, if we think forward, then the web browser can become more than just a tool for viewing content. It can actually become a way for accessing applications online. And there's a multitude of uses. Things like you've got a web browser, usually there's a camera attached, so things like augmented reality could become a part of your web page. Viewing sports online, we've got things like the Connect devices. Imagine if you could connect your Microsoft Connect device and actually through a web application be accessing that and building websites which take advantage of these cool new devices. Content creation is a big area which is always using the maximum amount of CPU power available from things like video editing, 3D animation, and motion capture. We'll be showing some demos around content creation in a second. And then there's problems such as engineering. And when you start looking at these problems, you think, well, isn't there heavyweight desktop applications which are used to do things like engineering or fluid flow analysis? You say, well, yeah, but they're also having the same challenges as everybody else. They're trying to use the multi-core CPUs. And if we can use the same power in the browser, there's actually a lot of secondary benefits to building a web application. Things like collaborative workflows where multiple people can connect and work with the same data at the same time. And then there's health and sciences, where the ability for multiple people in different locations to actually work with the same piece of data is super important. Web applications that can be used to communicate things like MRI scan information to patients in remote locations or even with doctors in other hospitals. Web technologies have a lot to offer everybody when it comes to building applications today. And of course in business we have things like financial analytics software for analyzing share prices. So enough of that. We're going to show a bit of a demo now on what we're up to. Before we start doing the demo, I want to say the stage we're at. We've been developing Fabric for about a year and a half. We're at the alpha stage now, so we've got our first customers coming on board. What we're showing you is just a snapshot in time. We're working pretty hard on it every day, so in a month we're going to have cooler demos and things keep progressing very quickly. So the first demo I'm going to show is actually something called an Nbody Simulation. And the reason we picked this because although it's an academic test, it's a sort of a stress test of your GPU. I'm going to miss the link. I know. So what this is actually utilizing your GPU to calculate galaxies forming over time. Every single point in this large constellation is actually exerting a gravitational pull on every other point. And it's an interesting problem to look at because it's numerically, well, the algorithm is super simple, but it's numerically incredibly heavyweight. And it's also an algorithm which is solved by lots of people using different platforms, so it provides a good benchmark. Just press play, stop there. So what we have is a true web application. It's using web tools and everything for the interface. We have a render region here. Just a second. And this is, we can interact with the scene and we can actually zoom through it. These controls here, although I can't see so well, there's some parameters there for the size of each of the stars, but it's the same content that would normally be, you'd normally build a desktop demo app for. You'd use a glut UI and you'd actually knock it up, but we've provided the tools that you can actually build this demo and run it in a browser, and then actually distribute it to infinite numbers of people. All they have to do is install the plugin. Yeah, and actually we based this demo on a demo from NVIDIA. So it's this very similar. We actually just made sure that we used the web technology for the UI. But apart from that, most of the code is exactly the same. I'm going to show a video now. I could have showed you this demo running on this machine, but I've got a nice quad-core machine at home, so I wanted to show it running on a more high-performance machine. And due to the video recording software that I'm using, which isn't obviously the best, we get a slightly jerky playback, but it is actually running super quickly. It runs at about 40 frames per second on my machine without video recording software. It's basically a flocking demo, so all of these particles are looking at neighboring particles and avoiding collisions and things like this. On my quad-core machine, I get a very healthy CPU utilization. There's acceleration structures being used to make sure we optimize all the lookups. But if we look closely, those particles, I'm just going to pause this for a second. If we look closely at those particles, they're not actually, they're avoiding colliding with each other, and they're doing sort of the basic flocking rules. It was a simple test to try. It's just sort of the beginnings of a crowd simulator. And as a crowd simulator, it could be used to say things like simulate the performance of buildings or large-scale architectural projects, where they want to see, well, what happens when we put 11,000 people walking through a building? How much congestion do we get at certain places? And these are real-world problems that people are working on today. So real-world statistics is that a single-threaded application wouldn't run at a fraction of this speed, even if it's written really efficiently. And with the numbers that we're getting, 11,000 agents running at 40 frames per second without video recording going. That's actually the same. That's as good performance as you'd expect from a handwritten, well-written desktop application. There's no performance difference at all. But the same application will run on Windows, Linux, and OS X, and even Android, without actually needing to change anything. As we go forward, I'm just sort of highlighting here the fact that we're using web controls. This is using, we use jQuery just to lay out the user interface. These buttons are just jQuery buttons. And we sort of use standard CSS just to build your UI. So HTML provides a really good, really rich tool set for building user interfaces, and JavaScript provides a really rich language for doing event handling. And that's what we do use those web technologies as much as possible. I'm just putting a breakpoint in this file and just refreshing the page because I want to show you guys that it really is doing things on load. It's not actually a pre-built demo. As the page is loading, and a dependency graph is being built, and we're actually doing a runtime compilation. The compile happens on load rather than at execution time. It's a compile on load, so we are actually front-loading the work in the same way when you compile an offline application. You're actually pre-processing code as much as possible, so at execution time it actually runs as fast as possible. Press play. There's a source code being pulled in here called flocking.kl, and that just includes the code that actually runs on each particle in the flock. And as I press play, basically that file got pulled in, compiled, and now it's actually part of our graph and it's running. Just a second. I don't have a lot of space up here. Okay, so this is a video. If I can show it full screen. Okay, so this is actually, before I get into this, our background is visual effects and games, so we just decided to do some quick tests with motion capture. So motion capture is a process where you have a room full of cameras. It's a really large room, and these cameras capture ultraviolet light. You put these actors in the room and you put light dots on them, and as they move around you capture all of this motion. So you're capturing large quantities of data, very high resolution cameras running at very high frequencies, and all of this data is correlated together to try and triangulate the position of each of these dots. Once all these dots are triangulated, you still have a lot more work to do, and that's sort of where we're coming in. So we're working with Vicon. We run a server, it's a Windows server, and basically it's running a live set. All of this data is being captured, they're triangulating the dots, and then they're actually transmitting that solved data across a network stream, and we're actually connecting directly to the live network stream and processing it further. So what we're looking at is the Vicon software. It's called Blade. We can see the actors there doing their thing. Now we're back on our Linux machine. So the Linux machine is connected to the Windows machine, and we're actually receiving the dots. And at this point we're just doing a very basic display of the dots. This was our first test. I have a video that I wasn't able to show today, but it shows from this point we take the dots and we actually triangulate bone transforms. We triangulate bone transforms for all the bones in the body, and then from there we actually drive a full character rig, including inverse kinematics and other tools, and then from that we actually deform a mesh. So the architecture of Fabric means that the developer who built this doesn't know a whole lot about multi-threading. He didn't actually have to know anything about multi-threading. The way he structured it, Fabric takes care of the multi-threading. It's actually a very efficient client for the Vicon data stream. And it's also super flexible because it runs in a browser, so they can actually connect to their Vicon stream anywhere from any device at all. And the system is efficient enough that we actually expect to get fully rigged characters with hair and anything else running on them in real time in a browser. So I've got a bunch of demos. They will cover different things. This is what our alpha testers are getting to play with today. I'm going to go up and show some other demos. Basic demos. Yeah, these are the ones that the beta testers don't actually get access to.
Because the resources we're using are probably
So what we have here is just a HD video stream being played back. So we just use a standard off-the-shelf video decoder software. We have a system called Extensions, which enables us to link in libraries from from third-party tools and actually then use them to stream in data. So the Vicon stream is actually using a Vicon SDK. Here we're using the MPEG Playback SDK. Stream this data in, and then it's in our engine running in the browser, and we can actually do things with it like we're just using OpenGL here to do filtering. It did not work. Oh, I don't know what's happened there. I am sorry. I'm going to have to show you the other demo. Yeah. Okay. Someone broke the filters. Okay. This video, once it's playing in the scene, we actually we'll go into a bit further how our SDK works, but we're building a full, what we call a scene graph. So a scene graph enables you to construct 3D scenes. What we consider is that we're building a low-level architecture for doing high-performance computation in the browser, but it's domain agnostic. It doesn't have anything built into it for doing any particular problem solving, just the concept of processing data. But on top of that, we can actually build architectures for solving very specific problems. And in this case, we're bringing in video, we're actually putting it on a sphere, and then that sphere is being rendered from a camera. So we're using a lot of OpenGL, and we're actually sort of just doing some simple processing. In the previous demo, I would have shown you it's actually fairly basic GLSL shaders for doing things like edge detection. In that case, because we're doing all of the processing on the GPU, our actual engine isn't doing a whole lot. It's just sort of setting up the GLSL shaders and running them. So it's not actually a great showcase of what our system is doing. You could actually do some fairly similar things using WebGL, but I think our system makes it a whole lot faster. So we're going to talk a bit more about how our engine does these things and how we've gotten to where we are. So what Fabric is it's a dependency graph. It's basically from within your running web application, you construct and manipulate a dependency graph. A dependency graph is this collection of nodes. Those nodes contain data, and they're connected together with dependencies. And the dependencies basically define an ordering of execution of the nodes. The actual modification of the data as it propagates through the graph is affected through operators. And these operators are written in a language we've been developing called KL. And this language, it's compiled statically, so it takes advantage of all the optimizations that you find in a statically compiled language. But it's being compiled on load, which means that it's actually platform neutral still. The web application is still a platform neutral web application. If you run the same demo on different CPU architectures, different machine code is generated, but it's generated on load. So the KL code is loaded in much the same way JavaScript code is loaded. JavaScript code is loaded as a web application loads, and from within your JavaScript you actually start saying, okay, we're going to be constructing this graph. It's got these nodes in it, and it needs this code compiled and these operators attached. We use a compiler architecture called LLVM, and LLVM is a really cool, great project, and it's being used by a lot of different companies today. The reason why we started using it is because it's actually got very fast compile times. We knew that absolutely it was important that we could compile and load our applications super quickly, and also has a great back-end architecture for sort of the optimization stage. So we knew that the code we would be generating would be competitive with sort of any other traditionally built application. And sort of the secret sauce of the way the thing that we've been building is the glue stuff that basically you can define your graph, you can define your operators, and once you've assembled them all, the execution engine just runs. And so design considerations when building the system is that by defining things using a dependency graph, we've automatically defined independent tasks which can be run on different CPU cores. So the graph implicitly defines task-based decomposition of your workload. And that works very well. For each node, we actually have data stored on the node. And what we have is a concept where a node can store a bunch of data, but that data can be a homogeneous data set, a large chunk of data, things like images and meshes. And this process using our operator architecture in pieces, so we can actually slice up that data set and actually allocate it to different cores. So at the same time, we've got task-based distribution of work. At each node, we can actually decompose that even further and break it into separate data chunks and allocate that to different cores. So that's why the system scales very well to many numbers of cores. At the same time, we're actually also working with the GPU. So we can actually push work to the GPU and let the CPU get on with doing other things. So we're actually utilizing the GPU whenever possible. At the moment, we use it mostly for rendering, but we're actually working on sort of utilizing the GPU more and more for sort of generic number crunching problems. So that's pretty much it for us today. Is there any questions? Sorry? Yeah, sure. I was actually expecting that, so. I don't quite have enough room to do things. So the KL language, Peter designed it. When we first started working on Fabric, we were actually supporting C++ in the browser, and we just knew that wasn't a long-term solution.
Minor security.
And while we looked at things like, Google's been working on things like native client to try and make C++ secure in the browser. It's also that's a huge problem to solve as well. So we decided that actually it was easier to develop a language which actually solved the problems we were looking to solve and nothing else. It's actually a fairly simple language. So a calc bounding box is a nice simple file. So this is an operator which runs on a piece of geometry to determine the bounding box for the geometry, just looking at the maximum and min values. So you can see the language we developed is strongly typed. All types actually have to be defined in advance. And but in many ways it's very similar to JavaScript. It's got a very JavaScript-like syntax for many things like for loops and conditionals. It's actually the intention is that a developer who's familiar with JavaScript can actually pick up KL and within a couple of days be fairly familiar and be able to write code. In fact, I've been working with JavaScript and KL so much that when I switch back and forth, I actually always have to sort of tell myself, okay, strong typing here, but that's pretty much the only difference.
Something for me as a build language is sort of an interesting question is like, how far can we take the language design to get away from the strong types? Because that is one thing that JavaScript programmers are not used to having to deal with. There's a lot of type inference you can do in a language, which is really nice, which is one of the directions that I'm sort of really interested in taking this language. But the point of the language is not to be as sophisticated as a language like C++, obviously. What we're looking for is something which enables people to do high-performance computation without actually having the humongous learning curve involved, because it's people who have specific problems, performance issues, which they need to sort out, and they don't want to jump too far from the web application development paradigm to do so.
So, I mean, KL stands for Kernel Language. So it's not a full language. It doesn't actually have to have as many features as a full programming language like JavaScript or C++. It really is just for developing kernels of code that run on nodes in a very well-defined context. Yeah, sure. So the question is, how would, if you're building a web page or web application which is using Fabric technologies, basically what extra stuff do you have to do? Like, how do you integrate it? So I can show you one of the demos that we've been looking at, just so you can see. Open up the flocking demo. And effectively at the top of our page, and you would have seen this, I think I stepped through it a bit too quickly in the talk, but we specify a bunch of JavaScript files. I mean, we're looking at compacting a lot of this stuff. We can actually merge our math files into one file. That's a longer term issue. But effectively, we have a bunch of 3D math here. We specify our scene graph system. So what the scene graph is it's a layer of code which abstracts the dependency graph. We see that a lot of people just want to build, like if we step through. So the first file that gets included is wrappers and JS, fabric.js. And when the web page loads, we actually invoke our plugin. We construct an instance of our plugin. So we're running things through an NPI powered plugin. Actually, I didn't mention that earlier, but yeah, everything's running in a plugin. The first thing that has to happen when we start constructing a scene is, where do we construct the camera? Somewhere around here. Okay. So as we can see here, there's cameras and lights being configured. And the fabric namespace actually initially sets up the context and prepares the plugin for actually constructing scene graphs. The scene graph is just one application of Fabric. It could be used in a completely different domain where 3D rendering is of no interest whatsoever. And then, of course, you'd use a different set of code, and you have a much different set of files being loaded.
So the short answer is through JavaScript.
Is there any question from VC?
How would we hear them if they had a question?
They would unmute them.
Okay. Do you guys have any questions remotely?
So, the question is more general about WebGL. There's obviously some security problem, drivers, and so on. What's your view on this in the long term?
That's an interesting question. So the question is, there are some security problems with GL drivers, which are a bit of a concern for WebGL. Like, what's our answer to that in Fabric? That's a really interesting question. Right now, we're exposing the GL bindings directly, so we have the same security issues. We would like to be able to expose things at a little bit of a higher issue. But one thing to keep in mind with Fabric is that there's the idea of having a consumer web application running Fabric to produce a high performance component, but there's also people who we see as being more initial customers for the product are people who are installing a specific application or something like that. So we can govern the hardware in the first stages of what we're doing. So basically, the long and short of it is that, this is sort of an ongoing, what is the best solution to this? I mean, I know you guys working on WebGL, it's a similar problem. What do you do about the problems with graphic driver and security? How do you manage the GPU memory, stuff like that? These are big things. But again, yeah, the typical initial Fabric applications are going to be, well, okay, yeah, this machine is actually going to have a specific NVIDIA card or something like that, and you're basically installing this as an application delivery platform for a specific application as opposed to a general web consumer thing. That said, we're looking forward to, okay, what happens if it actually does become something where people go to a website and, oh yeah, now they've got something running, which is, these questions need answered. This is one of the reasons that we're using Kale to do the high-performance code instead of using C++. There's nothing wrong with using C++ if it's something that you're asking people to install on their computer if they want to use the application. But we'd like something better than that in the long term. We'd like the possibility of being able to have untrusted high-performance code running for sure. It does for the high-performance code. But for the GL issue you're specifically answering, that's still sort of an open question on our end as well. To tell you the honest truth, what we'd like more than anything else is we'd like to just have access to the GL context. That would simplify everything tremendously for us, right? Leave that to the browser. The browser is extremely good at handling security. So one of the things that we're doing is we don't actually access any resources. Like people can't load files off of disks and stuff like that, obviously, right? We get all of our data through HTTP streams coming from the browser. That's great because then we inherit the browser security model. We'd really like to be able to do the same thing with the rendering pipeline, for sure.
Just to solve that problem.
Yeah. But you haven't solved it yet?
That's a feature request. So just to explain, the reason why KL provides a security layer is that a language like C++ exposes pointers, and pointers are basically addresses in memory, and they're really they're a loaded gun for a lot of developers. And by exposing such things in the browser, you actually create massive security holes. So by developing a language like KL, it's intentional that it's pointerless. You never actually access memory directly. You never need to allocate memory or deallocate memory. All of the memory management is handled using NKL automatically behind the scenes for you. We do expose a system called extensions, which enables you to link in a library. And when you're building an extension, you're writing it in C++, and you can do whatever you want there. And we use the extensions to connect to things like the Vicon stream or sort of video streams and other things.
Question that you said, do we have new language? The question about
So the question is, we've introduced a new language, so how does that affect the tools that people use? The first thing is that KL is compiled by the browser as it loads, so there's no specific tools required to work with KL. It's just a text file like JavaScript. So we use the same editors to edit JavaScript and KL at the same time. Once the application's running, we actually do have a debugger running that we can analyze the running application and provide tools to actually understand the performance and sort of identify bottlenecks and things like that. I can show the debugger. Yeah. I'll show the debugger just quickly. I'm going to go back up, sample, basic demos. Just come to this flocking demo.
Yep. You don't want me to do that. I can dance tango for you guys.
So I'm just opening up the console. Firstly, we can log stuff to the console, so that's an important debugging tool for a developer. You can actually just spit whatever you want out from the running KL programs. So we use that liberally just to understand what's going on. So notice the nice code completion, all those tools that we love very much from Google. And here we have our debugger. Now, as Peter said, it is at preliminary stages, and we're still working on things. It was actually a project that's high on our priority list to rewrite. But what we are seeing is a visual representation of the dependency graph that got constructed. Over here, actually, we have the flock, and a flock, or one particle system like a flock, is actually broken down into multiple dependency graph nodes. Each dependency graph node effectively defines sort of an execution context. So so all of the flock particles live in one node, but there's other data that gets associated with the particle system, like for example its bounding box, which is stored in a separate node. And this enables us to schedule the execution according to the nodes that you're running. And the scene graph system we're building actually abstracts that away. So as a developer, you don't actually need to know that one flock is made up of multiple subnodes. If I click on this flock attributes DG node, I can see immediately sort of all of the members which are assigned to it, and inputs and outputs that actually says dependencies. What are we dependent on, and what's dependent on us. We can also debug running operators, and the fact that we're running a compiler in the browser gives us a lot of flexibility. Like, we can actually run modified code as it's running, and it'll just re-jit the code. As long as the code doesn't syntactically break anything, basically the flock will just change behavior. So we see this kind of like edit and continue in Visual Studio. What we don't try to do is propagate those changes back into your source code, because we're not writing stuff to the disk. We use it as just a way to test out running code and fine-tune it. And then we put the code back in the source code, put the changes back.
So in terms of debugging at a lower level, which is kind of an interesting question for a performance-based language, this is something which I've thought about. There's actually absolutely nothing inhibiting us from basically doing breakpoint reflection from the LLVM environment back into the browser, which will be really fun to do once it gets to that point. But yeah, it's absolutely. I mean, LLVM is just a generic compiler structure. Like, we absolutely have the capacity of doing that. But I'm suspicious of, there's certain cases where that will definitely be useful. But I think for a lot of the problems that people are going to be solving, analytic tools are probably going to be just as useful. Just being able to do useful profiling is going to be a tremendously helpful thing. And debugging multi-core applications in general is a very difficult problem space. So those tools tend to be a little bit more useful in my experience.
Well, that's part of our work in progress. What our goal is to abstract the GPU to the point where the developer doesn't need to concern themselves with it. Our goal is that developers don't need to know a lot about GPUs. That's our goal from a sort of a business perspective. And we're not going to talk much about the technical side of things, just because it's stuff that we're still developing. At the moment, so any code that we use the GPU for, we explicitly manage the GPU. So we do expose the full OpenCL API from within KLs, and of course we also expose the full OpenGL API. So you can manage your GPU manually, just in the same way you would in a desktop application. What's nice is that because we expose the full OpenGL API right up to OpenGL 4.0, we've got access to things like geometry shaders, tessellation shaders, and really the latest and greatest hardware. And this is something we can do because we're not constrained by standards bodies. We're not trying to hit some lowest common denominator. We can actually push as hard as we like on this stuff. And for a lot of the customers we're talking to, they do have a very powerful GPU in their machine, and they would like to use all of it. So there's no reason for us not to do that.
Yeah, absolutely. Yeah, absolutely. I mean, so the question is, are there any limitations to the parallelism that you can extract from the operator graph? Yeah, of course. I mean, there are a lot of different multi-threading models that have different sort of efficacities depending on the problem domain you're working in. For the problem domains that we're sort of targeting, like building things around like high-end scene graphs and stuff like that for 3D, for instance, we're finding this actually works really well. There's already a lot of task-based and database parallelism in these scenes. If you consider, for instance, other types of applications, like we've had some questions from people around, for instance, using actor-based models for not multi-threading. It's a little bit larger at that point. And that definitely would be an alternative model that we could use in this case, but it's kind of difficult to do static analysis on that kind of stuff, which is one of the really big benefits we get from taking the operator graph approach to things. One of the things which is really, really powerful with what we've done here is that we have not just all the source code for all of the operators, but we also have a full description of what's necessary to decide how to optimally multi-thread things based on the currently available hardware. So in a sense, you have basically a transportable description of a computational problem. And it varies very specifically computational problems. This is something I don't think Phil mentioned. We're not expecting somebody to write their whole application in Fabric and Kale. It's more that, a web application, which is 95% JavaScript and all the other web technologies and stuff like that, has specific parts of it for which the existing high performance features of JavaScript just aren't sufficient. Things like web workers and stuff like that are not really very good for doing database parallelism and stuff like that. What we have is we have this way of representing the computational problem which needs to be solved in sort of like a package that can actually be transported from, like, it can be described within the web browser, targeted for the specific machine that it's running on. It's very easy for us to do a lot of static analysis on it. That's one thing we're already doing a lot of to figure out how to best run it, based on what hardware is available, based on other computational resources which can be made available, right? Yeah. But yeah, absolutely. There's no question. It's like there's a bunch of server cloud-based multi-threading models, which, yeah, I mean, they're trying to solve a different set of problems, basically.
There's also an important element that Fabric is really just a computation engine that's running in the system. We leverage the browser as much as possible whenever we can. So the browser has a very powerful event model for catching events and propagating through the web application. So we actually catch the browser events and translate them and use them in the 3D scene graph. So we actually translate sort of 2D the browser events into 3D events. And we actually have built up an event model in our 3D scene graph which mimics very closely how the browser DOM events work, including things like bubbling and stuff like this. So and then we actually do propagate those events back into JavaScript. So the idea is that we use JavaScript exactly for what it was designed for, event handling. And things like manipulation in any systems where we are actually interacting with a running graph, we're using the JavaScript engine a lot to do modifications to the running graph. So if you're going to be painting strokes on a mesh or making changes to the graph, every time you make a structural change to the dependency graph that's running, that change is actually made in JavaScript. And then the next evaluation that comes through on the engine, those new changes are in place. We don't allow any sort of structural changes to the graph while it's running. We sort of, in between frames of evaluation, we allow changes in the structure. Yeah, we don't actually, the technical level that we're aiming at is actually a web developer. Sort of, we want it to make it possible for a web developer who's not even familiar with things like memory management of any kind can actually build a high-performance application, an application which is competitive against a well-written desktop application. So a lot of these issues like memory management, the first goal was to actually keep that abstracted away from the developer, for multiple reasons, one of them being security, but the second one being simplicity.
Yeah, that's a good question. Sure, of course. I mean, what can I say to that? Obviously, yeah, if there's a bug in LLVM where it's generating absolutely incorrect code, it's referencing pointers the wrong way, absolutely. Yeah, I don't see that as being a different scope of potential security issues beyond stuff that exists, for instance. And yeah, I mean, obviously, the JIT in V8, for instance, could have exactly the same problems, right?
This is minimized by the fact that our interface with LLVM is really just the KL source code. We don't actually, so only through KL is the way that they can interact with the compiler. There's no other hooks provided.
Yeah, we're hoping the fact that, you know, I didn't write LLVM will inspire a little bit more confidence. It's a large public project, right? There's a lot of people auditing it. Yeah, yeah, it's pretty crazy. It's yeah. If there's anything, just sort of a side note that will sort of inspire how stable LLVM can be, it's how rarely they actually do bug fix releases, which is like never, because I've never seen so many unit tests before in my life, right? Basically. I'd be interested in hearing if you guys have had different experience.
You could have found one.
Have you? Okay.
Thank you.
I mean, there's one.
Okay.
You could layer on, run the output of this to an CL native client.
To a what? Native client?
Native client.
Oh, absolutely.
Yeah.
Absolutely.
An extra layer of security that.
Yeah.
That's actually. Can I talk a little bit about the native
Sure.
client stuff? Yeah. Absolutely, and that's something that we actually. Yeah. So the question was, Pia was pointing out that we could actually pipe the output of LLVM to native client. So essentially, we could target native client as the platform as opposed to a browser plugin. Well, honestly, that we'd like that. problem is native client's sort of been a bit behind. Like they've been reiterating on stuff quite a bit. I don't know if you guys are working on native client here. If you are, it's great to talk to. But no, it's like there's been a lot of iteration on it, and it's sort of like we've been trying to push ahead, and they've been sort of honestly lagging a little bit. And so we're like, okay, well, they're fundamentally what we have with Fabric internally, which would be sort of interesting as developers, is that it's actually a client-server architecture, right? So you actually need just a message pipe to work with the Fabric core. It's actually, and it's truly client-server. You can actually have multiple clients working with the same core, which is nice. It opens up a whole bunch of different possibilities. But we actually did that intentionally because we originally had more of an object-based, like methods and properties interface, which is what native client was using back in the day when we were first looking at it. And then at one point, we were finding, first of all, that the performance was absolutely abysmal for talking to the browser this way. And the other thing was that I think that they found exactly the same thing in the native client team. So we basically said, look, okay, let's go back to the drawing board. Like, let's make this so that they can decide to architect things in whatever way that they want to, and it's not going to kill us. Because we'd like eventually to make it so that we can just deploy on the native client and just say, hey, look, once again, Google's done all the work for us. They've sorted out the security issues and stuff like that, right?
I wasn't thinking so much necessarily at the NACL, the native client plugin or interface in Chrome as much as the machine layer rewriting and validation.
Yeah.
Machine
oh, I see. So we actually did like the pass. That's an interesting idea.
Like output native client approve x86 code.
Yeah, and then run your verifier.
Run your verifier on that, and then you have some decent extra safe code.
Yeah, absolutely. That's something we could actually enable just easily as a flag. It's like you're running extra secure mode. Yeah, sure. That's an interesting idea.
Well, we've been looking at native client fairly closely for the last year and a half and tracking its progress. And our intention would be to support native client if possible. It does actually eliminate one of the big problems that we have bringing a plugin to market, which is plugin install friction. And that's exactly why it was developed, right? So we actually hope that one day we can actually take advantage of native client. I think that's about it for today. Thanks, guys, for listening.
Thank you.